Hi all. Today we discuss an application of this partial derivatives. We already discussed in the last class how to find the partial derivative of a function z equal to f of xy with respect to x and with respect to y. Now we consider this question. This question in this video. The plane x equal to 1 intersects the paraboloid z equal to x square plus y square in a parabola. Then find the slope of the tangent to the parabola at 1, 2, 5. Okay, so first we need to identify this is a paraboloid. How will you identify this is a paraboloid? So first you consider this xy plane here. So I'll write this is x and this is y. This is x prime and y prime. Now consider at the point 0, 0, the value of this function is 0 itself. Okay. Now you consider a point on this, or if you consider z axis here, I'll draw the z axis. When you consider the z axis here, this is, suppose this is our z axis, then we need to consider this is our z axis, and you consider this is our z and this is z prime. For at the point z equal to 0, we can get set of 4 points 0 equal to x square plus y square. At z equal to 0, we have x equal to 0 and y equal to 0, because x square plus y square equal to 0. So the point at z equal to 0 is 0, and we consider z equal to 1, then the corresponding equation will be x square plus y square is equal to 1. Then this will give a circle. Okay, at the point z equal to 1 here, you need to consider a circle here. Okay. That will give a circle, and at the point z equal to some 4, then x square plus y square equal to 2 square, that is equal to 4. So that is again a circle. At the point, this is z equal to 1. At the point z equal to 4, we need to consider a circle with radius 2. Okay, so this is the at each of these points z, when you consider z is equal to 2, then there is another circle in between this. Okay, so you need to consider different circles with the different radius and different centers. Then this collection of all circles will give a surface like this. Okay, so this is what we called a paraboloid. That's why we consider this surface of this function z equal to x square plus y square. At each of the value of z, we can get a circle at this paraboloid. Okay, with the different radius and different centers. At z equal to 1, this is the center and this is the circle. At the point z equal to 2, this will be the center and the circle will be here. And at z equal to 4, we can need to consider this, and so on. So this will give a paraboloid. When you consider a plane x equal to 1, I'll call this is equal to, this blue color is the plane when x equal to 1. This cuts this paraboloid, and the intersection will be a parabola like this. Okay, we need to find the tangent, slope of the tangent at this point of intersection of parabola and this paraboloid and this plane. Okay, so the idea is how to find this. So in order to consider this parabola, we need to consider the equation of the parabola. That is the idea of finding the slope of the tangent in this point. Okay, the slope of the tangent in this point is, we consider this parabola as a plane curve, or as a curve in a plane. We can say that that plane is y and z. At x equal to 1, the plane is yz plane. Okay, yz plane at x equal to 1. So that is this plane, x equal to 1. In this plane, we have the equation. We need to find the equation of this parabola. So that is obtained by putting x equal to y in this equation. Okay. So once you consider that equation z equal to x square plus y square at x equal to 1, you can get this function. So this is the equation of this parabola. Okay, by putting x equal to 1 in this paraboloid. That is because the parabola is obtained by taking the intersection of paraboloid and x equal to 1. So by solving these two equations, x equal to 1 and z equal to x square plus y square, you will get this parabola, equation of this parabola. Then this is a parabola in the when you consider this is our zy plane, and here we have y and this is z. So this is the parabola 1 plus y square. Okay, like x equal to y square, we have z equal to y square. Okay, so we need to get at the point x equal to this at this point. This will be like this. For each value of z, we can get two values of y. So here we have -2 and +2 here. So this parabola is at the point z equal to at the point y equal to 0. We can get z equal to 1. So this is the parabola. Okay. This is that parabola. At the point, at some point of this parabola, we need to find the slope of the tangent. So that is the derivative of derivative of this function at that point. So to find the derivative of this point, this function, you need to consider d by dz by dy at the point. The corresponding point is here we have 1, 2, 5. So here x equal to 1, y equal to 2, z equal to 5. So y equal to 2 here. So here we have y equal to 2. Then this is the one way to find the slope of the tangent of this parabola at the point 2, 5. Actually, this is when y is equal to 2, you can get z equal to 5. So this is the point 2, 5 in zy plane. So this is nothing but the derivative of 1 is 0, the derivative of y is 2y, that is equal to 2 into 2. At this point y equal to 2, you can get 4. So this is the way we find the derivative of the slope of the tangent of this parabola. So here we use the idea of partial derivative to find this. Okay, how will you get the slope using the partial derivative? Okay, here we consider this curve by taking x as a constant. Okay, when we take x as a constant and treat this as a function of y alone, now you consider this derivative of this function dou z by this is dou z by dou y. Okay, by taking x equal to 1, x equal to a constant, then you can get when you put x equal to constant, you can our function varies over here. Yeah, the value of the function values over here. So that will give you the corresponding parabola. So when you take this one, you can say that the derivative of this x is x square is 0, because we are considering this x as a constant, x equal to 1, and we'll take the derivative of this quantity, that is 2y, at the point 1, 2, 5. That means x equal to 1, y equal to 2, and z equal to 5. So that will give at the point 1, 2, 5. So this contains only y, so that is equal to 2 into 2, that is equal to 4. So this is the this is an application of partial derivative to find the slope of the tangent at some point of the surface. Okay. Next we have another question. In this question, this x, y and z are independent variables, and f of x, y, the function is if we call w is a function, w is equal to dou f of x, y, z, that is equal to x sine y plus 3z. So these x, y, z are three independent variable rather than two independent variable, and find dou f by dou z, or you can consider dou w by dou z. Okay, so how will you find this? In order to consider dou f by dou z, or this is same as dou w by dou z, if you consider this is equal to w, then we need to consider the other two independent variables are constants. Okay, so this is the derivative of this expression by taking x and y are constant and the y z is the only variable. Okay, now you consider a dou f by dou z, that is equal to x is a constant, so you never consider the derivative of this, x times a derivative of this function. Okay, derivative of this part is cos of y plus 3z, and you should multiply this quantity with the derivative of y plus 3z. Okay, then what is the y derivative of y plus 3z? By taking y as a constant. Okay, that means the derivative of this expression by taking y as a constant. So derivative of y is 0 and derivative of 3z is 3. So this will give, that is 3x cos y plus 3z will give dou f by dou z. That means taking x and y as constant and z as variable, you consider the derivative of this expression. Next we have next question. This is the 7th example in the textbook, that's why I put 7 here, and this is the 6th example of the textbook. Please don't mind to name this as 7 and 6. In this question we have if resistors of R1 and R2 and R1, R2 and R3 ohm are connected in parallel to make R ohm resistor, the value of R can be found from the equation 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. When you connect the resistors in parallel connection, you can get this is the resultant resistance. So we need to find out the rate of change of the total resistor as far as R2 is concerned. Okay, so the rate of change of R with respect to R2. When this R2 varies, then what is the rate of change of this R? At R1 is equal to 30, R2 is equal to 45, and R3 is equal to 90. So in order to find this, first we write the expression of dou R by dou R2, the partial derivative of R with respect to R2 at the point 30, 45, 90. These are the values of R1, R2 and R3 respectively. So how will you find the first expression? So we are considering R1 and R3 as constants. So we can find the derivative of this as 0 and the derivative of this quantity 1 by R2, that is minus 1 by R2 squared plus again 0. So this is the derivative of R with respect to R2. But this is possible when we write this R is equal to this expression. But here we are given this is not R, this is actually 1 by R. That means this is not of the form R is a function of R1, R2, R3. Okay, so this is not of this form because we can consider this as the implicit form. Okay, so to find implicit form, you need not consider this. Okay, we need to consider the derivative of the whole equation. Okay, to find this, you consider the derivative of 1 by R. What is derivative of 1 by R? So you just remove, you never follow this, and we consider this is the derivative of 1 by R, that is minus 1 by R squared times dou R by dou R2, that is the derivative of R with respect to R2. Now you can get that is equal to, this is 0 and the next will be minus 1 by R2 squared times this dou R2 by dou R2, that is equal to 1. So the last time will be 0. So this dou R by dou R2 is equal to, this expression is equal to, by taking this minus 1 by R squared to right hand side, you can say that is R squared divided by this one, that is equal to we can consider R2 squared. So this is the partial derivative of R with respect to R2. Now we need to evaluate this quantity at the point 30, 45, 90. So we consider this at the point 30, 45 and 90. Okay, so this is equal to, this R squared can be written as 1 by R is this, then R squared can be written as by taking the reciprocal of this and taking the whole squared, then put the values for R1, R2 and R3. That is, we need to find R, then we will evaluate, we put the value for this R2 and taking R squared. So this is R by R2 whole squared at the point 30, 45 and 90. Okay, so first we can evaluate R. The expression for 1 by R is 1 by R1, 1 by R2, 1 by R3. So 1 by R is 30, 1 by 30. So this is 1 by 30 plus 1 by 45 plus 1 by 90. So this will give, by taking the LCM, here 90 is the LCM. So this is 3 plus this is 2 plus 1 by 90, that is equal to 6 by 90, that is equal to 1 by 15. 15, 6 are 90. So 1 by R is equal to 15. Then you can consider R is equal to 1 by R is equal to 1 by 15. That means R is equal to 15. Now this takes the form 15 divided by R2 is given by this 45. So 15 by 45 whole square, that is equal to, what is 15 by 45? That is 1 by 3. 1 by 3 whole square, that is equal to 1 by 9. So this is the value of partial derivative R with respect to R2 at the point 30, 45, 90. Okay, so one thing you should remember is there is a temptation to write like this, dou R by dou R2 from this expression. But you should remember that that is possible only if this R is a function of R1, R2, R3. Here, if the function is not in R, in order to get the expression of R, you need to consider the derivative of these functions. The reciprocal of this function. So when you consider the reciprocal first, then you try to evaluate the derivative. That expression will be much complicated. You will have to use the quotient formula and all. So this is the easiest method. So this is the implicit form method. So that is the easiest way to find the derivative of R with respect to R2. Okay. Now we have an interesting problem. So this is very important because this gives a interesting result on partial derivatives. So this example 8 explains there are functions for which partial derivatives exist, but f is not continuous. Okay, the continuity means limit when you consider the function f of xy, and if you consider the limit xy tends to x naught y naught, and if this coincides with f of x naught y naught, we can say that this function is continuous, otherwise not. So in order to find the continuity, we need to consider the limit. Okay, so this is the function in the xy plane. So when you consider x naught y naught here, then there are so many paths to approach this x naught y naught. So if you consider all these paths, and at all that time this f of xy tends to f of x naught y naught, we can say that this f is continuous at x naught y naught. That is the idea. So once you define this function f of xy is equal to 0 when xy not equal to 0. That means one of them is 0, you can get this product is 0. That in that time the value is 1. Otherwise, if x and y both are non-zero quantity, we can say that the value is 0. Okay, so that is the surface like this. So we will verify the continuity and partial derivatives of this function at the point 0, 0. So by finding the first part, find the limit of f as xy approaches to 0, 0 along the line y equal to x. Okay, so once you consider y equal to the line y equal to x, you can say that there is a line like this. This is the line y equal to x. And how will you find the limit? F of xy is constantly 0 along the line y equal to x, because y equal to, when you consider all the points of the straight line x comma y with y equal to x, you can say that this contains only the point 0, 0 whose coordinate, one of the coordinate is 0. Okay, then all other points you have this x and y are non-zero quantities. Therefore, all other points you can get the limit, the value of that function as 0, because except x equal to 0 and y equal to 0, you can get this xy is always non-zero. Then the function value is 0. Okay, so when you approach 0, 0 through this line, we can say that all these points we have the function values 0. Okay, so the limit xy tends to 0 0. Along this way we can say that the function value is 0, therefore the limit is also 0. Okay, but we know that, so this shows that limit xy tends to 0 0, f of xy is always 0, that limiting case is 0. But at the point 0 0, what is the value? At the point x 0 0 we have x equal to 0, y equal to 0, then this product is 0, the function value is 1. So f of 0 is 1, f of 0 0 is 1, but the limit is 0. Okay, so we can say that this never happens. So this limit is 0 0, the value of the limit is 0 and the function value is 1. Okay, so we can say that 0 not equal to 1, then this function, this proves that f is not continuous at origin. Okay, the limit exists but it is not continuous at origin. Okay, but when you find the partial derivatives at the point 0 0, that means partial derivative of f, dou f by dou x. Okay, at the point x equal to 0, y equal to 0. So when you consider the partial derivative of f with respect to x at the point 0 0, we need to set y equal to 0 always. Okay, this is the point 0 0, so we need to take y equal to 0, y is a constant, that is y equal to 0. Then if you consider y equal to 0, you can say that the function value is always 1. Okay, so we can say that dou f by dou x at x equal to 0, 0 is the dou by dou x of 1, because the function value is always 1. So this is equal to 0. The partial derivative exists with the partial derivative with respect to x exists at the point 0 0 as 0. Okay, similarly when you consider dou f by dou y, that is again dou f by dou y at x equal to 0, y equal to 0, we need to set x equal to always 0. X equal to always 0 means the product is always 0. Again the function value is 1, so this will be the derivative 1, that is again 0. Okay, so this shows that the partial derivatives of these two functions with respect to x as well as with respect to y exist, and it is 0, and those are 0, but this f is not continuous. Okay, so there is no direct relation between partial derivatives and continuity of this function.